At this point, we've learned a lot about the coefficient of determination. We've learned that it's the r² value, and then that means that it measures the strength, though not the direction, of a linear relationship between two variables. We also learned that it has this more formal interpretation, where it measures the proportion of total variation in the response variable that is explained by the least squares regression line. From there, we were able to use the interpretation of strength, as well as just the straight up interpretation part down here, to gauge which are the strongest and which are the weakest relationships, both in terms of the coefficient of determination as well as the graphs or the explanations. What remains to be seen, however, is how to calculate the coefficient of determination. So let's try to do that now. We're going to take this data set, which we've seen before. This is the percent of students that are on free reduced lunch and the percent that pass the math test at various schools in the Sandusky, Ohio area. So I'm going to grab the calculator. I'm going to press Stat, number 1. I'm going to go up and clear out this old data. Up, clear, enter. And then I need to, press Stat 1. I need to be able to see my numbers here, so let me move this over. And then I'm going to enter our values. Oopsie. Hold on one second. There we go. I don't know why I was doing that. So 29, 29, 23. I think 15 is the last one. Yep, 15. And then we'll go right and enter all these other values. All right. Once we have all the data entered, then we need to be able to come up with the regression equation. So you go to Stat, move to the right to Calculate, and you want to pick number 4, which is linear regression. Same place you would go to get R. Now our data set has L1, so second 1 is where the X variable is. L2 is where the Y variable is, and we in this course almost always leave these next two things blank. So leave them cleared out and then go down to Calculate and press Enter. And there's your r² value right there. It's 0.473. So let me write that right here. By the way, some books capitalize R and some books don't, so don't be worried about that. If it's capitalized or not capitalized, it's the same thing. Computer programs tend to capitalize it because it's easier for it to code with a capital letter. So either way, it's 0.474, roughly. All right, so that's how to calculate it. What if it was already calculated for us with Excel? So you can see here that Excel has done the scatter plot and also given us the regression equation and the r² value. And technically that y should have a little hat on it because it's the approximation. It's not the actual y. The actual y values are all the data points, or the data points y values. So y hat is our approximation, which is our equation right here. So we have our y hat value right there, and we have our r² value. So notice that it gives the coefficient of determination, which is r², automatically. Okay. Now, how could we compute the correlation coefficient from this given graph and information? Well, remember that r is the square root plus or minus. It's one or the other, so it's plus or minus the square root of r². Now, it could be positive or it could be negative. It depends on the situation. So it could be plus or minus the square root of, and then our value was, sorry, it's up here, 0.5803. 0.5803. So I need to find the square root of 0.5803. And I will use a calculator for that. So press the square root's above the x² button. So press second x², and then 0.5803. And I get 0.762 roughly. So I should put an approximation here, 0.762. Okay, now which one is it? You have to make a choice. It can't be both of them. So in this case, it's actually r is equal to, in fact, let me close this out. And then I'm going to say, in our case, R is equal to, not equal, approximately, negative 0.762. Now here's why. If you look at the slope, or if you look at the regression line, or both, you can see that this line is a negative trending line. And you can see it in the slope because the slope is negative 0.5 or 5.03. So we choose the negative R value because the slope of the regression line is negative. And there we go. All right, now what kind of relationship and strength do we have with this? Well, let's see here. It appears that we have an R squared value of 0.5803. Let's go back and remind ourselves where that falls. So 0.58 is right in the moderate zone, right here in the blue zone, close to that 0.6. So that would be a moderate relationship. We can't comment about the direction from R squared, but we can comment on the strength. So it appears to be a moderate linear relationship because R squared equals 0.5803 is between, what were the numbers, 0.64 and 0.25, I want to say. Yep, between 0.64 and 0.25. Sorry, zooming past, is between 0.64 and 0.25. All right, now we want to interpret R squared in the context of the situation. That's where we get the percentage of variation. So we can say that 58.03% of the variability in the Y variable, and Y variable was life expectancy. So in the life expectancy from country to country, i.e. the Y variable, can be explained, or is explained, I guess, is explained by the least squares regression line, or the line of best fit, or the linear regression line, whatever you want to call it. All right, a politician from another country sees our data and results for life expectancy and fertility rates. She determines that to get a longer life expectancy in her country, she should just restrict the number of children to 1 per woman. What's wrong with her reasoning? Well, there's a lot of things wrong with that reasoning, but she is inferring a causal relationship between fertility and life expectancy. Right? That is, she thinks that lowering fertility will automatically mean that life expectancy goes up, just magically. In reality, of course, that's a very poor decision to make. It's a very poor idea because there are a lot of things that are affecting the life expectancy in different countries, right? Let me write that up. All right. So, of course, in reality, there are a lot of lurking variables. That's our fancy word for hidden factors, hidden things that are going on that aren't accounted for in our data set, that could be affecting both a country's life expectancy, a country's life expectancy and their fertility rates, such as education, the healthcare, the infrastructure, whether or not women have power in relationships in that society, etc. All of those things affect life expectancy and fertility, but they're not showing up in this graph directly. They're showing up in the graph indirectly, right? Our line does a pretty good job of modeling what's happening. It shows about 58% of the variability can be explained by that line, but there's another 42% that we don't really know why it's going on. And that's partially because of these hidden variables that are behind the scenes affecting what's happening. All right, let me put in that 42% business right here 1 second. There we go. 41.97% of the variability cannot be explained by our model, which is quite a bit. Right? It's not tons and tons, but that's why it's only a moderate relationship, because there's quite a bit of variability here that we can't really figure out what's happening. And again, it's all due, well, not all, but it's mostly due to these lurking variables and other things that could be affecting the results here. All right, we're all done with the coefficient of determination. I'll see you back here to talk about residual plots.